Hello and welcome back to the channel. In this practical video I'm going to show you how to set up a pre-compliance test for conducted emissions using a Keysight EXA Spectrum Analyser as well as an AC LISN and a DC LISN. So we're going to use 3 different pieces of equipment and 2 test setups. A line impedance stabilization network, or in other words LISN, is simply a low-pass filter placed in series with your power supply, be it AC or DC power supply of course, and this filter, all function that it has is to output an RF signal that is produced by your device into a RF output, which is typically has a BNC type of connector, and then it connects into a spectrum analyzer or an EMI test receiver in other words, and this basically gives the measurement for against the limits that are specified in CISPR 22 or CISPR 32 sort of emission conducted emission standard, as well as of course FCC CFR 47 part 15b unintentional radiators. So this is the basics of the conducted emission testing that we're going to perform. And if you look at the block diagram of a line impedance stabilization network, you'll see that it is nothing but an inductor, which is a 50 microhenry in this case, placed in series with the power supply, and it has a capacitor on the output which provides a high frequency path for RF signals to go into EMI test receiver, where we're going to measure them and compare against the limits. So the main function of a LISN is to provide a precise impedance match to the device so that we can get exact measurements of the noise that is going back from the device into the supply. So this is a very simple setup with AC LISN. And basically the DUT is powered through it, and I've done a little life hack by just connecting the earth or RF ground of the LISN to the socket through this filter. So effectively it's an additional filter on the earth ground. It's not really going to make much difference. What I'm sort of doing here, which is a bit unusual, is I also use a UPS to power the LISN and the DUT, and that is because this LISN keeps tripping RCD. Since the LISN has a high leakage current, it's tripping the RCD and switching off the power supply in a building, so that is quite an issue. But whilst using the UPS, I can run it for about 30 minutes of the UPS, which is sufficient for me to capture the data. So the data is captured through the monitoring BNC cable, and then that's plugged into the RF input of the Spectrum Analyser. And here is the Spectrum Analyser itself, in which case is the Keysight and 9000B, so it's a rented Spectrum Analyzer. And basically what's good about this box is that it can allow you to even set up a preset for different measurement standards, such as this one. If you didn't have the setup, it's very simple, because the frequency, so the first thing you would do, you would set up the frequency from 150K to 30 megahertz. That is a typical frequency range for class for CISPR 32 and CISPR 22, and basically the conventional conducted emissions on AC. So Then you would also need to set up the bandwidth, and the resolution bandwidth is very important to set it to 9 kilohertz here. So this is the range. So you can sometimes have it at 100 kilohertz, and you will see that it acts much faster. It takes a lot less time to go through it, but the resolution is not going to be as detailed. So this is really good to set it to, because this is also in a standard, to low frequency. The other important things to sort of look at is the peaks. So yeah, in these settings, I've set the detector to peak, but depending on what you're looking for, because this analyzer in principle can even do quasi-peak, but the quasi-peak wouldn't work very well. And yeah, because you have to really reduce the window. When you switch to quasi-peak, you're only looking for specific points, right? And then you reduce your bandwidth, so you make it so narrow that it's basically can only be analyzed to get the exact value of the peak at this position. Typically in EMC test houses, this is done with software. Usually for debugging, I would either use the peak or average, because we have average limits as well for the test. And when I do that, I typically also set the trace to trace average as well. And in this case, this is pretty much ready to go. Unfortunately, the mains in this building are not very isolated, so this is why I'm only showing this as an example of a pre-compliance. So we have, due to other equipment being switched on, we have quite a lot of noise. And specifically, if we go to the marker, we can find actually, it's confusing why it can't find it, but yeah, there is a very strong peak at 13.5 megahertz, and this is caused by an NFC reader that is enabled somewhere in the building on this ring main circuit. So this is basically the noise, and that's not going to go away unless I isolate the mains for the LISN, which I don't have the equipment to do. So what I'm going to do is I'm just going to save this trace to view, so that is the noise floor is saved. Then I'm gonna switch to the trace tool and create basically a new trace, create new measurements, and now we are more or less ready to make a scan. We want to use battery backup. You can hear everything's got a lot of noise straight away. And you can see we have about 35 minutes. So in terms of limits, we have about 10 dB margin in this case. So again, we can output a peak table. There you go. So now we have all the various peaks that came out, and we can see that we are significantly below the limit, which is 60 dB microvolt at this frequency, and 66 dB microvolt at about this frequency, at low frequency, and 60 at most of it. This is for class A emissions. So I can now save this result, and that is effectively the pre-compliance scan done. And then what you can also do, you can set that trace to view, separate trace 3 and switch the LISN from one conductor to the other. So that's the second conductor now. And you can see it's not all too different whatsoever. Basically, if you detect any kind of abnormalities during this scan, you would then try to investigate and introduce filters like this one or like this one and so on. So the peak 2 is at 150 kilohertz, and you can see it there, but I know this is also caused by poor calibration on this particular LISN, so I'm not too worried about it. In the essence, you can see that most of it is matching the noise floor, and most of the emissions actually are coming very low, and this isn't any kind of concern, so I'm quite confident that this device is going to pass the conducted emissions test now. So that is an example of pre-compliance with the AC AC LISN. I do apologize. The other thing we can do, we can also add an attenuator to the signal path, to the LISN output, and basically that was the issue with the overload, and you can see the error is gone now. So adding this attenuator helps to remove potential issues, and overdriving the Spectrum Analyser, which can be a problem, so it can destroy the Spectrum Analyser. It still comes up occasionally. Then the final thing to say is that when you've done the measurements, when the measurements are complete with the LISN, what you should do, you should disconnect it first before powering off and disconnecting the mains from the LISN, because when you disconnect the LISN from mains, it can discharge into the Spectrum Analyser and damage it. There you go. And here's the screenshot of the final measurement that I took in this setup. And something I forgot to talk about is that when we look at the final measurement, we should account for the attenuation of the signal. And as you saw, we were using 10 dB pad in the as a physical attenuator on the input to the Spectrum Analyzer. And additionally, in the settings, you've got 6 dB attenuation in the Spectrum Analyzer itself, so we must correct for 16 dB attenuation when we consider our results. So for example, in this case, where we have the tallest peak at the frequency of RFID, that we need to add 16 dBs, and we will get approximately 57 dB microvolts, which is very close to the limit. However, we can exclude that because this is permissible as per ETSI EN 301 489-3. We can set up exclusion bands for conducted and radiated emission measurements. However, when we look at the peak, for example, number 3, which is a genuine emission, and we add 16 dBs to our measurement here, we will get 52 dB microvolt, and that is significantly below the limit, but this is the actual number that we need to record. So it is the 57 dB microvolt, and then we compare that against the limit, not the numbers that you see on the screen. Now let's take a look at the DC LISN, and basically DC conducted emissions. So this is a very simple device made by TechBox. So the source is written there, maximum 60 volts DC and maximum 10 amps. So that's why it's really small and portable. So you'll see that this test setup is a lot easier than the one we've done previously with the AC LISN. So first of all, you're gonna need a battery power supply or some sort of a DC voltage power supply. So this is what is going to be used. So it's just gonna output 24 volts, this is the only connection that you need. There's no need to ground this device, unlike the AC LISN. So that's already making it simpler. And the first things first, before we even plug in the DUT, it's good to capture the noise flow of the LISN. So this is what I typically do. Is you can already see that there is some noise in the basically noise floor of this building, because again this isn't particularly isolated. So you could capture that. So if you see there's 460 kilohertz in the noise floor, then you shouldn't be surprised when you actually measure it with the DUT. And one more time, we already done this, but as a measuring standard you can set it here, or you can set it to a different standard such as mil, for example, and basically you can adjust it like so. Anyway, we're gonna stick to CISPR32, and if I wanted to, I could adjust frequency and the bandwidth using this feature. Then, and also in this you can set up limits for your test, which I know at class A CISPR32 is going to be around 60 dB microvolts, and by the way, we are in dB microvolts, so you could also play with this setting and set it to dBms if that's more convenient to you, but I'm going to stick to dB microvolts because that's what's in the standard. Alright, so this is effectively the capture, so we can capture that noise floor, and then yeah, I always average it. Oh yes, and detect, in this case I was using peak, but I think for the best results of conducted emissions you should be really using average peak detector. So now it's actually taking average of average is not really point, there's not much point, so it's already taking average when you're doing average detector. So that's good enough, and now we can without powering the DUT. I'm not going to show the DUT itself, by the way, because this is a bit confidential, so I'm just going to say that this is a 24 volts powered DUT that is going to be installed in a vehicle. So it's a very typical voltage supply for a vehicle electronic subassembly. And you could watch my video where I explain the standards that apply to electric subassemblies to be installed in a vehicle environment. So now this is the noise that's coming from the DC cable itself, or rather getting picked up by the DC cable itself, which you can actually somewhat see. This is the cable, and it's just in the air. So, and we know that it's the case because we can put another marker, do peak search, and this is a typical RFID frequency. In fact, I know it is 13.56 megahertz. It's all over the building. So this cable is picking it up from a bit of a distance, and as well as the rest of the noise. So this is also the noise floor. So when we take a measurement, we need to be careful that we're not considering the noise floor. So again, I'm gonna make this trace view, and I'm gonna create yet another trace. Do all the same things that I've done before. Okay, and now we are ready to actually power the DUT. So you can see that we have yellow trace, which is a noise floor without the LISN, without the DUT of the LISN, and then we have the blue trace, which is a noise floor with the DUT, but not powered on. Now we can actually power on the DUT. You do that, you start seeing that it's drawing some power, and now we've got the actual emissions from the DUT. So this is effectively the measurement. This is the emission from the DUT, and we can see that the marker is showing us that the main center of this emission is at 4.5 megahertz, which is quite high at 54.3 dB microvolt. In fact, that's most probably going to fail the test. So we can also do the usual another delta on, for example, another marker. So relative to marker 3, and pick search. So we don't want this one, but we want this one. So that delta gives us 418 kilohertz, which is the switching frequency of one of the DC-DCs in this DUT, and I know that because that's a known problem. So then, once we've done that and we've done playing with this, this is effectively our result. There is no positive and neutral for DC. There is only one scan, and once we're finished, we can just do pick table as we've done before. And now this is effectively our final output, so we can see that there are the 20 most noisiest peaks, which we can then compare against the limits. In this case, I'm not using the attenuator for RF input because it's not needed, and there's no need to also use any voltage battery like I did with AC mains, because that device doesn't actually have any leakage current or anything like this. So it's a very smart and easy device to use, and you can use it to test any DC voltage system, even something powered by USB, for example, at 5 volt DC. You can use this device, which I highly recommend. And then we've got the similar result of DC LISN scan, as I showed previously, and this time I've had a preamplifier enabled in addition, and the attenuation was set to 30 dB. So when we want to compensate for the amplitude, we need to take 20 dB off the attenuation value, so it is going to be 30 minus 20, and then we're going to compensate for 10 dB by adding 10 dBs on top of our recorded peak values. So in this case, the highest peak value was 54 dB microvolt, and if we add 10 dB microvolt to it, we will find that we are in fact 4 dB over the limit, and that is actually corresponds to the real measurement. So this is basically what you have to do when you do this sort of analysis. You have to always compensate for the attenuation and the amplifier gain if you have amplifiers enabled. And that's about it for this video, where we've covered the first test setup with AC LISN, where we used an uninterruptible power supply because this LISN trips off the RCD in a building. Ideally, you don't really want to do that. You want to isolate your LISN from the mains, and so that you use the isolator box, which is a dedicated piece of equipment, and then you will have a very solid noise floor that you can compare your measurements against. Unfortunately, in my case, that was not the case, but never mind. And then we covered the second test setup, where we used a DC LISN, and we basically done the exact same measurement, but on a 24 volt and 0 Hz DC supply. And the only thing we haven't covered in this video is a three-phase LISN, but really that is just the same sort of device, except it's rated for higher currents and basically matched to 3 conductors rather than just 1. So it still is the same sort of thing. You get a single output for your noise measurement, and you just have a switch where this output is connected to each phase. So when you create a 3-phase conducted emission measurement, you're going to get 4 graphs this time, because you're gonna also measure the ground. So that's about it for this video. I hope you found it very practical and useful, and if you did, please check out my PCB for EMC page, where I provide links to online courses that I developed for radio test setups and also upcoming vehicle test setups. So these courses are only available through my website, so please feel free to purchase and use the discount code RF50 for 50% off. And that's it for today. Thank you very much, and I hope to see you very soon.